Hello students, welcome to today's lesson. We are going to look at expansion and contraction of solids, liquid and gases. We start with expansion and contraction of solids. In this case, when we talk of expansion, this is a process of increasing in size or volume when that solid is heated. And contraction is a decrease in size or volume when that substance or that solid is cooled. So the mass of the solid does not change. So when we are changing or when we are expanding or contracting, the mass does not change. But what changes is the volume. And when the volume changes, it implies that also the density changes, because from our definition, we know that density is mass per unit volume. So if the volume is changing, also the density is changing. So it implies the density of the solid increases when the body is cooled because the volume decreases. And it decreases when the body is heated because the volume increases. Then we need to look at some experiments to show or to demonstrate expansion and contraction of solids. We start with the first one, the ball and ring experiment. In this case, we have a ball and ring. In the first step, we test whether the ball is passing through the ring when they are at room temperature. We test, we allow it to pass. Then after that, we are supposed to hit this ball away, ensuring that this ring is not heated. Then we allow it to pass. Then after that, you leave this ball on the ring and observe what will happen. We have our observation here. When the ball is heated, it does not pass through the ring, but when it is left on the ring for some time, it passes. What is our explanation? When the ball is heated, it expands, that is increasing in size or volume, and that is why it cannot go through the ring because it has expanded. But when it is left on the ring for some time, the temperature of the body decreases, it gets cooled, and therefore the ball contracts. At the same time, the ring absorbs some heat from the ball because it is a good conductor of heat. Its temperature rises and it increases, and so it expands, and therefore it increases in size. So these two cases, or these two, ensures that the ball will pass when it is left there for some time. Then we have the other experiment. We have the bar and gauge experiment. We have the figure below. Now, before you heat or at room temperature, you find that this metal bar will fit on the gauge. It will fit on the gauge. What we are supposed to do is that we are supposed to heat this metal bar away from the gauge and then come and try to fit it. Then we have our observation. In our observation, we have that when the bar is cold, it just fits into the gauge. When heated, the bar does not fit in the gauge. So what is the explanation for that? The bar expands when heated, and that is why it is unable to pass through the gauge. Then we have an example here. We have the diagram, that is our bar and the gauge. Then we need to explain what would happen when the bar is heated and you try to fit it in the gauge. As we have seen in our experiment, the bar does not fit in the gauge because it has expanded. Then the second question on the same. Consider a case where the bar is slightly bigger than the gauge at room temperature. Explain what you will do to make the bar fit in the gauge. Remember, we are saying that the bar is slightly bigger. So in that case, you're supposed to heat the gauge so that it expands, and therefore it can allow that bigger bar to fit. Then the next one, we are going to compare the expansion and contraction of different metals. And this case, we have the illustration here. We have a metal bar that is fitted here in our clamp. We have a pivot. In our pivot here, we have the pointer, and down here we have the scale. This will give us the expansion. So the metal that is being tested will be fitted here, then it is heated, then the pointer will give us the scale. So different metals will be fitted at different times, and you will be able to get the scale. That way you will be able to know which one is expanding more and which one is expanding less. So that way you are able to get that the metal bars of the same size made of different materials are attached on one at a time and heated for the same length of time. The readings on the scale are recorded and compared. So that way you are able to get which metal bar is expanding more and which one is expanding less. But when you are doing this experiment, you need to take some precautions. One, the metal should be of the same length and diameter. Number two, the metal should be heated using the same burner. And number three, the metal should be heated for the same length of time. Then we move to linear expansivity. And this one is the tendency of a material to expand when heated. Different materials have different linear expansivity, meaning that the rate of expansion or contraction are not the same. So this linear expansivity is measured in a unit that we call per Kelvin, as shown in this table below here. We have a case where we have aluminium. The linear expansivity will be 26 times 10 to power negative 6. The same case to brass, you have 19 times 10 to power negative 6. So these one are giving us the value of linear expansivity, and as you can see, it is different for different metals, but for the concrete and steel, they are the same. So we move to what we call the bimetallic strip. This one is made of riveting two different metals of different linear expansivity. So it implies that one metal will expand at a higher rate than the other. So at room temperature, you will find that the two will have the same size, but when you change the temperature, the size of each metal will be different, and therefore our bimetallic strip will curve depending on which one is expanding at a higher rate. For example, if we take a case where we have brass and iron at room temperature and pressure, you will find that they will be having the same length. But as you can see, the brass has a higher linear expansivity than iron, and therefore brass will expand at faster rate than iron. So it implies that when the strip is heated, the brass will expand more than iron, as shown in our diagram here. We have this diagram. So when at room temperature, they are of the same size. When it is heated, as you can see, it is expanding more, the brass is expanding more, so it curves. When it is cooled, again the brass will contract more, and therefore it curves like this. So the figure below, that is another example. The figure below shows a bimetallic strip at a room temperature, that is 25 degrees Celsius. We have the bimetallic of aluminium and copper. Draw the same bimetallic strip when at 90 degrees. So we have our diagram when it is at 90. As you can see, aluminium will expand more than copper because aluminium has a higher linear expansivity than copper. So we have that when the temperature increases above room temperature, aluminium expands at a faster rate than copper. Then another example, draw the bimetallic strip the same when at negative 25 degrees Celsius and explain your observation. So when it is dipped at a negative 25 degrees Celsius, it will curve like this, which implies that as the temperature decreases below the room temperature, aluminium contracts at a faster rate than copper, and that is why it is curving like this. Aluminium will expand more than copper. Then we move to expansion and contraction in liquids. In this case, we are going to consider the figure below. We have the beaker or the flask that is containing water. We can see the level of water here. Then we are heating. So the flask, when it is heated, it is observed that the water falls slightly and then start rising. So what is the reason for that? The initial fall of water level in the tube is due to the expansion of flask, which gets heated first. So it expands and it increases the volume, and therefore the level of water falls slightly. But then when the water starts expanding, it will expand at a faster rate than our solid here, that is our glass, and therefore the liquid will rise. Note that different liquids expand at different rates. So if you use the same, or if you have the same experiment but you change the liquid, that is, you can use alcohol or mentholated spirit, you will find that if you heat for the same time, you will find that the temperature or the mentholated spirit will expand most, followed by alcohol, and finally water. Then we move to expansion of gases. So in gases, we are going to consider the following illustration. We have water, we have inverted flask here that is containing air. So what we are supposed to do is that we are supposed to warm the flask. You can warm it using your hands and then observe what will happen. So it is observed that the level of water inside the glass tube drops, indicating that the air has expanded. As it expands, it will push the water inside this tube. Then, when the flask is warmed further, some bubbles are seen at the end of the tube in water as air escapes from the flask. So that way we can be able to show that air is expanding when heated. But when the flask is cooled, water level is observed rising up the glass tube. As it is cooled, it reduces in volume, and therefore water will rise to occupy the space. And this is because the air inside the flask contracts and it creates a space. Then we move to molecular explanation of expansion. From the particulate nature of matter, we know that matter is made up of particles, and these particles are arranged, and the arrangement gives us the three states of matter. We have solids, liquids, and gases. So in solids, the particles are closely packed, and the force of attraction between them is very strong. So these forces are so strong that molecules do not change their position, but when they are heated, they just vibrate about their mean position. So as they vibrate, they increase, or what we are saying that the vibration of the molecules increase, resulting in increasing distance from their mean position. So when they increase their vibration, because they have gained kinetic energy from heating, you find that at the end, those particles will occupy a larger space, and this will give us a general increase in size or volume. Then we come to liquids. In liquids, the forces of attraction between molecules are weak, or they are weaker than in solids. Hence, the particles are further apart. So when it is heated, the vibration of the molecules becomes more vigorous, and therefore the liquid will occupy a more space. The same case applies to gases. The particles in gases are further apart, and they have very weak force of attraction, what we call the cohesive force. So when they are heated, they gain more kinetic energy and they move further apart, and this will ensure that they occupy more space, which will lead to increase in volume. Then we have assignment. In this assignment, they are just testing what we have just read. So ensure that you go through your video and listen so that you can be able to grasp all concept, then attempt the assignment. So thank you, and let us meet in our next lesson.